change the resolution of what the camera records? Do this. So hopefully that'll do it. But I've reduced it a couple times and it still keeps turning off. Here's the board. Hopefully that will work. So many people rely on that camera just from a count, like half this class comes. So hopefully the camera will start going better. So I'm backing up to the beginning of this chapter to go through all this. The rest of this chapter is you look at the structure of the energy levels in an atom, and we talk about how light interacts with that. A lot of chemistry these days, if you go into a lab, rely on what we call spectroscopy. Simple definition of spectroscopy is how light interacts with matter, but really what we mean is how light interacts with atoms, because atoms is what matter is made of. And over the last, I don't know, starting early 1900s to present, more and more techniques of using light interacting with matter have been developed. And there's massive amounts of techniques now where you can take a sample that has atoms in it, of course, and hit it with light in some way, study what bounces out of the sample, and you can tell exactly what's in the sample. But we won't go too deep into spectroscopy, but the basics are what we're going to cover. I need an eraser. So I'll use this. But I'll start with, do you remember what I said last time when I said you want to make the electron configuration of some atom? What do you start with? You walk up and you go 1, 1, 3, 1, 3, 5. Okay, just do that to get started. Those are easy to do. 1, 1, 3, 1. Try to make these straight. 1. That's still not straight. 3. 1, 1, 3, 1, 3, 5. That gets you started. You could get that by reading across the periodic table too. You shove helium over into that notch over there. You would get your 2, or you get your first one there. And you would end up going to the next row, and that would be this one. And then you go across to this side in the P block, and you would get these. But like I said, if you could just remember 1, 1, 3, 1, 3, 5, you sketch those down, you can get started on building an electron configuration of any atom. Once you get above here, you'd have to be reading off the periodic table. And maybe if you can remember it, there's one more 1 there. So that was the 1s, the 2s, 3s, and the 4s. This would be 2p and 3p. The 4p comes next. But I'm going to back off this very general view, because almost everything in this, well, pretty much everything in the earlier sections of this chapter talk about how light interacts with matter. And any specific examples we always use the hydrogen atom, which only has this. There's no electrons up here. And for these, well, let me say this before I erase. let's say you have this. So there is the electron configuration of hydrogen. It's only one electron in that first orbital. And I mentioned at some point last time that these configurations we're making are called the ground state configurations. The alternative is an excited state. Let me do this. Let me just, I'll get away from the hydrogen atom for just a second. So an excited state would be, here's the ground state. There's a certain amount of energy in each one of these electrons. An excited state would be, this electron would pop up here. Let me do it all the way up here. So now there's this sort of gap between all these electrons and this one. That's an excited state. So in the ground state, they're all stacked on top of each other. In an excited state, this one has been brought from here to up here. And let me say this, what it takes to make an electron go from here, just in its most fundamental fact, is energy. Yeah, put some energy in to make this pop up here. So when we say a ground state, we mean ground state of energy. An excited state means a higher level of energy. So an atom that looks like this versus this, that's the electron configuration of sodium. Ground state sodium, and then excited state, some excited state for sodium might look like that. You can get energy in by electricity. You can do it through heat. You can do it just physically banging atoms together. And you can do it one other way, by exciting it with just light. So light interacting with matter spectroscopy. Let me go all the way back to hydrogen now, because we almost always, it's really a consequence of the complication of quantum mechanics that in an introduction to this type of stuff, we just stick to the hydrogen atom because it makes it completely simple. And we won't go beyond the hydrogen atom. You'll see it feels very complicated. But so let's say this is hydrogen, and I want to erase this. When we do this, you can kind of forget everything but these S, because it's way more likely that an electron, when it gets excited, ends up in these S orbitals. So now hydrogen atom, we excite it somehow with energy somehow. There's one excited state it could get into. If you put, picture it having this level is some, I'll say E1, energy 1, and it takes a little bit, it's a higher level of energy to have the electron at E2. That much energy supplied between E1 and E2, we'll get it here. And of course, I would call this the energy 3, energy 4. So if you put just the right amount of energy for this gap, it'll pop up here. All right, instead of drawing the electron in there, what we usually do to indicate these, we call them a transition. It goes the transition from the ground state up to, say, this energy level. Instead of drawing the electron, we do that. That's saying it's gone from here to up here. So that's indicating an electronic transition, because energy went in and it popped up to here. It can also do the opposite, drop back down. So if the electron was here and then it dropped back down here, you would indicate the transition that way. So you with me so far? Electronic transitions. You can even do this. It can go there as a transition from E3 to E2, or 3s to 2s. I guess I'll leave those there. So electronic transition is really where we're going here. And of those different ways that you can make energy go in, we're going to focus specifically on energy going in as a light. A photon comes in, hits this atom, boom, and let's say it's just the right energy to pop it up to here. So this indicates a photon of light coming in, hitting the atom, and boom, that pops up there. So it happens in order. We're here at the ground state, and here comes a photon. Bang, this pops up here. It might stay there for a little while, and then it might drop back down to here. And when it drops back down, the energy leaves as another photon. That's how it works. So a photon comes in with just the right amount of energy. It'll pop the electron up to one of these spots. It might stay there a while, but it'll eventually drop back down, and a photon pops back out. With me so far? So to talk about photons in light, we have to discuss the wave nature of light. So I've got here, we have what we call frequency diagram. So if you wanted to map this out, you've got this sort of waving going on. And actually a photon, as it travels, it has an electric and a magnetic component to it that's constantly waving. It can wave at different frequencies, but what this is showing you is what we would call a full cycle. Going from up here, going back down, back up, that's one full cycle. You can see down here, this indicates a full cycle to there. So it goes back to its original state. That's why we call it a cycle. Frequency means cycles per second. So this is traveling along at the speed of light. And if you pictured this whole red line shifting to the right, and let's say I had kept my hand right here and it started to move to the right, the time it takes for this to end up here, if this red line was moving, however many seconds that takes, that's cycles per second. That'd be one cycle in X number of seconds. So however many cycles per second is the frequency. The symbol we use for that is kind of a fancy looking V, pronounced mu. And I'll say 1/s per second, cycles per second. I guess you should say cycles, but that's kind of, the cycles are implied, so it's usually just done like that. Another thing you can tell by these two different frequencies of light is what we call the wavelength, lambda. I'll say lambda. And this is in, we almost always use nanometers, but problems you'll get will sometimes say meters and you have to convert to nanometers. So this is saying wavelength of 2.0 meters and a frequency of 1.5 times 10 to the 8, 10 to the 8 cycles per second. The question here is asking you, it's saying here's a wavelength, this lambda is 2 meters, and they're trying to indicate that this is right in the middle here. So this peak lines up here. So this lambda is 1/2 the length of this lambda, but it's twice the frequency. Can you see why it would be twice the frequency? Because you get through a full cycle in 1/2 the time as you get through a full cycle here. So this is just a diagram that gives you a conceptual grasp of it. See if let me ask you this. Do you know what it, at least in the band of electromagnetic radiation, that is photons, that we see, what does the frequency mean? You guys ever heard this? So we see blue and yellow and red. Based on what I just said, what is the difference between blue, yellow, red? Okay, maybe you've never heard that, but it's color. I mean, it's, yes, color, it's frequency. So this little band of electromagnetic radiation, this is saying all the different frequencies. Like there are photons with that kind of a wave, and there are photons with that kind of a wave, and there are photons with this kind of a wave, and the difference is frequency and yes, wavelength too. But this would be different colors. So this is saying different wavelengths. You can also discuss them as different frequencies. Electromagnetic radiation with this range of frequencies is radio signals, microwaves that cook our food, and also I think cell towers work on microwaves. Infrared, and then you have the colors we see. Our eyes respond to these frequencies, aka wavelengths. And then there's ultraviolet, X-rays, gamma rays. This is useful for some of the questions you'll get. Again, I'll give you that on a test. You don't have to memorize it. But one thing to know, what's not there is energy. So I would say these are the three characteristics that you could look at a particular photon and say, here's its frequency, here's its wavelength, and thus there's the energy that's in this one photon. So now we're getting closer. There's a certain energy that goes with each one of these photons. These will be different energies, just like they're different wavelengths and different frequencies. But I brought up energy now to point out that, yeah, the photon has to bring energy in to pop an electron up somewhere. Or I should start doing this. And I want to say that, I would say this. Let me write it this way, just so you see it together once. High energy means high frequency, which means low wavelength, or short wavelength. I'll write it this way. High energy means high frequency, which means shorter wavelength. So you've got if I wanted to do it in a picture, there's a photon, and you can kind of see its frequency and wavelength there. But a lower energy, relatively, and a lower frequency means longer wavelength. And if I wanted to draw a picture of that, this is what I mean. So peak to peak, there's your long wavelength. And if this is traveling the same speed as this, aka the speed of light, then as this moves to the left, it takes a while for this peak to get over here, whereas peak to peak over here is this. So this has a higher frequency, which means higher energy. The more it goes back and forth like this, that's the energy. How much energy there's in this. This goes back like this, that's lower energy. And this is always true, relative to each other. If I didn't have this and this, and I said, hey, here's a photon, here's another photon, A and B, and I would say, which one has the higher frequency? This one has the higher frequency. I'd say, which one has the longer wavelength? This one has the longer wavelength. Which one has more energy in it? This one has more energy. It's just worth seeing that qualitatively. So all the different Frequencies, aka wavelength, aka energies, are what's being indicated here in this band. And this tiny little bit right here is what we see with our eyes. Okay, I'll leave it there. So we can sense electromagnetic radiation with our eyes in that one little band. Okay, so this is just a specific iteration of these. Let's say this says infrared, length 10 to the negative 6. So it's just saying somewhere in this range is infrared. All right, so did I walk past that equation? So this equation, I'll write it on the board. So worth, and I'll give you these equations on a test too, like on a back page like I usually do. But when it comes to a photon, which equation? Wavelength frequency, okay. Wavelength and so C, I want to put these where I can keep them. And there's a reason why we use C, because it's a constant. The speed of light is a constant. Light always travels the same speed. I need to see what units they give us. 7.99. I think they use 8. Do they not give it to us here? Gotta have it somewhere. Okay. They will use meters per second. So that's a constant that we'll use in our equations. Okay. So if you have this equation, just erase this. The question here is asking oh, there it is. Okay. So sodium. So this is saying, I'll say one has what happens here is you stimulate the sodium somehow. Sodium lamp is sodium vapor confined with some kind of electrode in there. All lights work this way, all light bulbs work this way. Sodium, so you have one electron here, and all these electrons are still here. But what happens is you stimulate the sodium, this electron up here pops up somewhere and stays there a split second, and then drops back down. And when it drops back down, it lets out a photon with a specific amount of energy, therefore a specific wavelength and a specific frequency. And the thing about this is these distances, you can think of these as distance from the nucleus. Do you remember last time I said what this is really diagramming is, let's make it smaller. 1, 3, 1, 3, 5. And here's the nucleus, and what I'm really saying by these is saying at the 1s, okay, that's a circle around a dot, but what I mean is a sphere around the nucleus. And this is just the distance from the nucleus. Same with this S, it's just a little further away from the nucleus. So that one is that far from the nucleus. All right, so these transitions that I'm talking about are essentially distance from the nucleus. And the point is here is whatever distance the 5s is from the nucleus, and whatever distance from the nucleus the 3s is, that doesn't change. Wherever you find sodium across the galaxy, those don't change. So the point is, there's a certain amount of energy here, and there's a certain amount of energy here, and E5 minus E3, whatever that is, this gap, I'll say ET for transition. Actually, we would do this. 5, write it bigger. 5, the transition from n equals 5 to n equals 3, that amount of energy is the energy that that photon is going to have no matter where it is in the universe, no matter what's going on with it. If you stimulate it and you pop this electron up to here, when it comes back down, it's going to be a very specific energy, therefore a very specific frequency, therefore a very specific wavelength. So this is why you can have a sodium lamp and it has sort of a yellow color. So it's giving off a photon in that visible range, in the yellow range. I didn't back up and say that. So this little band right here, it's showing you the colors. So this is saying the wavelength is right about here. Right here, where's the wavelength? Right about here, where that yellow band is. That's what sodium does. And it will always do that because these energy levels don't change. Those are the energy levels for a sodium atom. There are no other energy levels for a sodium atom. Meaning you will never see, okay, I'll say this. If you had a transition from here, it'll be a different energy and a different wavelength, but it will also be one little specific spot, and it will be in the visible range for these. So this will be a specific color, a very specific energy for that transition. There's a very specific energy for that transition, and so on from E6s down to here. Let's say it went from here to here. That also has its very specific energy. So what you see, it's just that most of the transitions in a sodium atom will be the one that's yellow. But there are a few other transitions that can happen. It's not necessarily 5 to 3. It could be 4 to 3. It could be 7 to 5. Any of these where it comes down, it's going to emit a very specific frequency, a very specific color. It just so happens that yellow is the strongest. So when you do this to sodium, it's going to look yellow. So we call those line spectra. If you took a prism that splits the light out from a sodium vapor lamp, you'll see a band right at the yellow, you'll see a band right here, a little band right here, and nothing in between. Meaning, you'll never see whatever the gap is from here to about here, whatever that energy gap is, you're never going to see that. There's just very specific, a handful of very specific frequencies that you'll see come out. You see what I'm saying? This is kind of the heart of spectroscopy. Why you can identify specific atoms or specific molecules by the light that comes out after you stimulate it with energy. Okay, so let me do the calculation. So this is setting, so I'm going to use this formula. and it's giving us, what does it give us? It gives us the wavelength in nanometers. So it's giving us this. This is a constant, so we already have it. And it's saying, I guess it's saying, what is the frequency, right? What is the frequency? So the calculation is going to be, what will we do? So one quick step of algebra gets you there, and then you just solve. Actually, these are the easiest thing to do here, since we have to be in nanometers, is a separate calculation, 10 to the 8 meters in 1 second. But I need to convert that to nanometers. So I'm going to go meters, nanometers, is 10 to the 8, no, 10 to the 9, right, for nano. 10, I did that backwards. I could do 10 to the negative 9. Let me do this. 1 meter is 10 to the 9 nanometers. So I'm going to convert this to nanometers per second. So basically, so 3.0 10 to the 17 nanometers. So if I wanted to change this to nanometers, that would be 17, and now I can say nm. I need to use that because I was given this in nanometers. So we'll use that for the speed of light. Um, 10 to the 17 nanometers per second over 5.89 nanometers. So the nanometers are going to cancel, and we'll have seconds on the bottom. But I would do it like this. Let's say 5.89, no, 589. Did you follow what I did there? I just took these numerical values, I put the 10 to the 17 out by itself. Now if I grab my calculator, divided by 589, calculator says, my calculator says but I still got times 10 to the 17, 1 over s. That's a correct answer, but it's worth doing scientific notation here. So 1, 2, 3. If they're going to approximate to 3.0, might as well put another 0, just so we can keep 3 significant figures. Times 10 to the 1, 2, 3. So that would be the frequency here, if I kept 3 significant figures. I'm used to books that go, instead of 3.0, they go 2.9989, which gives you more significant figures. If you have a constant that's always the same, you might as well use more significant figures than that. Yeah, they kept 3. Oh, they did use 0, 0. See that? Anyway. Oh, in case you don't know, let me put this into this equation here because it's kind of a fundamental equation that we can use. One of these chalks is darker than the other one. So, people watching the video, speed of light. All right, so what that means is, whatever the transition is, the main transition for sodium, it goes like that and shoots a photon out. It will have a wavelength of but it has that for its wavelength, and it has, oh, I erased it. 14. I'll write 1 over S. All right. What I wanted to say is, the 10 is on the bottom, so this is negative. 100 equals 10 to the 2. Just 10 equals 10 to the 1. 1 over 1,000 equals 10 to the negative 3, just like 1,000 is 10 to the 3. We bring the 1,000 up to the top. We change the sign, get that. So if you have units on the bottom, like 1 over S, it will sometimes be depicted as S to the negative 1. So don't let that throw you off. I tend to just stick to 1 over S. It's easy enough to write. Maybe that works better when you're typing. For a second. All right. All right, 1.5 times 10 to the 10. If you had this in front of you, 1.5 times 10 to the 10 is going to be somewhere in here. No, 10 to the 10. This one's asking if you had a frequency of 1.5 times 10 to the 10. So frequency 10 to the 10. Frequency's down here. Here's 10 to the 10. You're in the microwave region. That's what that question's asking. If you have this in front of it, you just read it. You read wherever you are. If it said you had a wavelength of 10 to the negative 8, then you'd be somewhere around here between X-rays and ultraviolet. Oh, nice. So I said I'd give you that on a test. You don't have to memorize this, which is why I'm sort of elighting this question. It's just, you just read it straight off that chart. All right, so this section was all about describing light, frequency, wavelength, and energy. You can relate frequency and wavelength to energy through that equation. So that is the wave nature of light. So quantized energy and photons. So I'll write Planck's constant now. Another thing we use a lot of. So it's a dark chalk. I guess so. So another constant. I'll give you this on a test. I'll give you these constants on a test. Let me write Planck's constant up there. Without describing a whole bunch of crazy stuff from quantum mechanics, quantization of energy is just saying energy always comes in this amount, these packets. You can't transfer energy. Here, let me write this first. Equals 10 to the negative 34 times 10 to the negative 34. The units here are joule seconds. energy seconds. When energy flows, and you notice how tiny this is, it's a tiny, tiny amount of energy. But you can't get 3.3 times 10 to the negative 34 units of energy ever transferred anywhere. It's weird, but it's taken us about 100 years plus to figure this out. It's where quantum mechanics really comes from. This idea that energy only comes in these discrete packets. Well, without overthinking it, we get this new equation. So now we've got Planck's constant, a frequency, and you can get an energy. So now if you have frequency, you can figure out what the energy is this way. The way what this extends to our discussion is, that's what this is saying. Energy doesn't go to any, you can't go up in energy any tiny amount that you want. You have to go up in these discrete amounts. So if there was an axis here that said energy, these distances up are integral values of Planck's constant. But let me get to energy of a photon. Here we go. Okay, yellow light again, the same thing that you would get from a sodium lamp, 589 nanometers. So what this is saying is, let me go back here and get that number. They're going to use sodium again. We figured out before that 5.89 nanometers and 589 nanometers gave us a frequency 5.09. So there's the frequency of that wavelength coming from a sodium lamp. There's the wavelength. What would the energy be? I'll say sodium lamp. There's our wavelength. There's our frequency. What would the energy be? That's what this next question is asking. E equals h nu. So we're going to use this now, and I guess you have to calculate the frequency first. I guess they do it in two parts, that's fine. Algebraically, you can connect those two things. That's supposed to be lambda. We've got that, and we've got E equals h nu. If I solve for frequency, this is E over h. If that's true, then so you can relate these together, but let's do it in stages, that's fine. So this is saying, first you would calculate, we're again given, which is lambda, but we need the frequency, so we first have to get that as a frequency, and then we can get energy this way. We'll use the constant and that frequency, and then we can find energy. This one might say, hey, you already solved for. So yeah, same thing. So you solve for what we did before. So that's this, what we just solved before. And now that you have that, now that you have that, energy equals H negative 34 joules seconds. That's J times S. We usually just put a dot there. You saw me use that dot when we would go grams, degrees C, when we did heat capacity. It just means grams and degrees C are on the bottom together. So now we've got joule seconds times our frequency. .09 times 10 to the 14, 1 over S. And you see that the S will cancel, will be in joules, which is what energy will be in. Me doing this, I would rearrange it. It depends on your calculator, but I would just do this in my calculator. 6.626 times 5.09, and then times 10 to the negative 34, times 10 to the 14. And then my units are joules seconds times 1 over seconds. So my units are going to be in joules. This, negative 34 plus 14. Is that 20? Negative 20? That's right, isn't it? Negative 20. And then this, I'm going to do it with my calculator. And we can fix the powers of 10 after that. Times 5.09, my calculator says, we'll be in 3 significant figures, so 33.7. 10 to the negative 19 joules. That should be the answer. 37. 10 to the negative 19. Yay. My brain's not tired yet. All these powers of 10 start to feel kind of unwieldy. Yeah, but let me point out what that comment is saying. We ended up with that for energy, that for wavelength, and our frequency was 5.09. All right, so there's the 3 things related to the photon. That's its energy, that's its frequency, and that's its wavelength. Let me draw this again. If you have these transitions and the electron goes from some higher S to wherever, down to here, and a photon comes out, based on the nanometers, we were able to figure out these 2 things. So this is saying the photon that comes out of that sodium lamp has a wavelength of 589 nanometers. It has 3.37 times 10 to the 19 joules of energy in it, and 5.09 times 10 to the 14 is the frequency. The photon coming out because of this transition. That energy, let's say this was 5s and 3s, and this would say energy of an electron at level 5, that n equals 5. This is saying .37 times 10 to the 19 joules. This gap in energy, this has a certain amount of energy, this electron, as it goes around in the atom. If it's up here and it's going around the atom further away from the nucleus at a higher energy level, it has its own energy. when the energy changes from this to a lower energy, the difference is what's being shot out here and this amount of energy. See what I'm saying? Follow that? So that's where the energy for the photon comes. It's the difference in energy between wherever it started and wherever it landed. The transition. Joules per photon. Okay. I'm just staring at the way they did those units. If you had a whole mole of sodium atoms, and each atom shoots out this much energy, you would take Avogadro's number, 6.022 times 10 to the 23, multiply it by this, and that's how much energy comes out of a whole mole of sodium atoms. The way they're using units there threw me off, but I guess we can do it that way. One mole of sodium atoms, one photon per atom. There will be this many photons coming out of that 1 mole sample of sodium atoms. And if each one has that many joules, joules per 1 photon. This many photons for 1 mole, but 1 photon is doing this. You can calculate the energy that comes out of a whole mole. And I suppose if you do the math here, you get 2.03 times 10 to the 5. .022 times 3.37, 20.29414 is what my calculator says. Oh, did I get 10 to the negative 19? Yeah, I did. Didn't I? That's what I had, 10 to the negative 19. 23 minus 19, I get us 10 to the 4. And I'm going to do a 3 here. Rounding, getting rid of that. Joules per mole. Photons cancel, joules per mole. Energy per mole of sodium atoms. And I guess they finished out to with the proper standard scientific notation. So it becomes 5, 10 to the 5. Anyway, so if you want to calculate a whole mole, it's ultimately multiplying this number by 6.022 times 10 to the 23. So you can do this on a per mole basis as well. All right, types of questions to solve. I'll solve this practice exercise. What I have in the back of the book for you to solve are just like these practice exercises we're doing. So it involves these things. Practice exercises 6.2. Well, I thought they gave us answers to those somewhere. Let me see. Additional exercises. Any of you guys scrutinize this book enough to know? I thought they gave us the answers to these practice exercises somewhere. All right, maybe not. All right, whatever, I guess not. But let me solve this one. Okay, a laser emitting light at a frequency of 4.69. So frequency wants to know the energy and times 10 to the 14. Whatever S. So what is the energy of this? We're given this, so we're going to have to first solve for the frequency and then use the frequency here. So the frequency, or no, we're given the frequency. Is it asking for energy? Yeah, so we can just use this. So energy times our units are going to be in joules because the seconds cancel. Times 4.69 times 10 to the negative 34 times 10 to the 14. 34 minus 14, we're at 20 again, 10 to the negative 20. 6.626 times 4.69. Three significant figures, so I'm keeping that. So it'll be 31.1 times 10 to the negative 20 joules. Negative 19 again. We're in the visible light, so we're staying in the same range for all these. That's what this comes out to be. That should be the answer to that one, if I didn't screw up. All right, that's the energy per photon, really. When we do these calculations, that's per photon. So if you had that many photons, you would just multiply. So let me make sure that's clear. I guess I would rewrite this as negative 19 joules per photon to solve this next one. If that's how many photons we had, 5.0 times 10 to the 17. Joules in one photon times 5.0 times 10 to the 17. and it's me solving it. I'll split it up the way I do. Times 5.0. So we're going to be in two significant figures, and then times 10 to the negative 19, times 10 to the 17, and I'll just joules. This will be 10 to the negative 2, negative 19 plus 17, and then of course, our calculator says, but we really are down to two significant figures because of that. So I guess this is just going to be 16. Those. And scientific notation will say 1.6 times 10 to the negative 1 joules, aka that's not in scientific notation. That's not in scientific notation. That's in standard scientific notation. Actually, all of these, at least those two, those are in scientific notation. That's standard scientific notation. All right. Let's see what problems I decided would be solvable for these two. Double check them. All right, I have here, well, let me write these down and then we'll double check them and make sure I picked out those. It's still on? Far so good. Don't screw with it. All right. Got 6.1920 21. Section 6.1, these I have from section 6.2. And I also have section, maybe I'll do that one more section before we look at these problems. Look there real quick. Gives us one more equation. So these are line spectra. We'll do this next week in lab. Actually measure line spectra. So if you had a neon, we always do these with lamps, at least for these simple types of experiments. But if you had neon gas in a lamp with the electrode, and you had the light come out, and you split it from the prism, all these specific lines are what you see. And those are indicating all these different transitions, but you don't see anything in between. So you get no light out of a neon lamp of these nanometers, or here. You only get these because those represent those transitions from up high to down low. And hydrogen there too. We'll do a handful of these in lab next week. So those are the line spectra. You ever heard that helium was not discovered on Earth? You ever heard this? We knew there was a spot on the periodic table where something should be, but no one had found it on Earth. But we studied when spectroscopy was understood and this type of stuff was understood, we looked at the light coming from the sun, and there it was. We discovered helium on the sun first because of the spectrum that comes from the sun. This is the other equation. It introduces another constant. This is called the Rydberg constant. Again, describing where all these comes from, I just never think it's really worth the big discussion. So RH, I've got that one written down, don't I? 1.09, yeah. So another constant, 96776 7, and this one's in 1/meters. It's worth having that one in nanometers too, I think, but let's see. And then you have this equation, 1/the wavelength equals the Rydberg constant times 1/n1 squared 2 squared. The 1s and 2s are about, there's one more equation that's related to this one. This one. N squared. This is how you calculate the amount of energy in a particular level. So when I was doing this, I was doing, let's say that was 3s and this was 5s, and I was saying the energy in 5 and the energy in 3, that's what these are. That's what this energy is. Like if there's an electron just sitting here going around the atom, that's how you calculate the energy in it. And I'm pretty sure I gave you some of those to solve too. And N is that principal quantum number I was talking about last time. Give me something to solve. I guess this equation too, but it comes from, all right, so if I had some energy, I want an example really. And let's just say I'll say that's energy 1, and this is energy 2, and you had a transition like that. So you could calculate those two energies and then do a subtraction. But notice energy of 2. 1 and 2 means initial and final. So these subscripts here, I could have a little I right here for the 1 and an F for the 2. So in equations like this, you can use 1 and 2, or you could use I and F. But it's going to be final minus initial.